Hello, everyone. Welcome to my talk. My name is Timur Doumler. I am a developer advocate at JetBrains. We make the C-Line IDE, ReSharper, lots of other cool developer tools. So if you have any questions or feedback about those, then I do want to talk to you. Please come and find me. I'll be around all week. Now we come to this talk. And a little disclaimer. So this talk is actually not the kind of talk where, I've solved the problem. Here's a finished implementation. It's on GitHub. It's all done. Go and use it. It's more like work in progress. So this is a problem I've been kind of working on and off for a while. I'm kind of still very much in the middle of solving that problem. I've figured out a lot of things. Still haven't figured out some other things. So it's kind of a snapshot of where I am right now on this journey. So if you have any feedback or ideas how I could do things better or what I might have overlooked or whatever, then please interrupt me or come talk to me or ask questions here during the talk. I think CppNow is actually a really cool place to do this kind of thing. So yeah, this is just a little disclaimer. OK, so what's the problem we're going to talk about? Lock-free atomic shared pointer. Thank you very much for turning out for such a, I would say, relatively niche topic. But it's a very interesting problem that has been bugging me for a few years now. So lock-free atomic shared pointer. There's kind of three parts of this problem, right? We're going to talk about all three. Let's start with shared pointer. We're at CppNow, so hopefully everybody knows what a shared pointer is. Does anybody not know what a shared pointer is? Cool. So just very quickly, that's what the standard says. It's a smart pointer to an object, usually obtained by a new. It implements semantics of shared ownership. And the last remaining owner is responsible for destructing the object. So you're going to have a ref count. The very simplest way you can imagine how this works is you have a shared pointer instance. That's the stuff on the left. And it kind of just has a pointer to this thing called the control block. And the control block is the thing on the right. And it has the pointer to the actual object. And then it has a ref count. And then it has the actual object itself, which might or might not be inside the control block. That depends on whether or not you've allocated the thing with std_make shared. Now, if you have that shared pointer and you make a copy of that shared pointer, you're going to get another instance of a shared pointer, which is pointing to the same control block, right? And then if you do that copy, then the ref count is going to get incremented. So you're going to have 2. If you then delete the copy, the ref count is going to go back to 1. If you then delete that instance as well, the ref count is going to go to 0. And then at that point, the object is going to be deallocated. And then eventually the control block itself is also going to be deallocated. That's how a shared pointer works, right? We all know this. Let's come to the second part, atomic. Now, atomic and lock-free are kind of very different things. Let's talk about atomic first. So atomic comes, as I'm sure many of you already know, so I'm just going to whiz through this very quickly. Comes from the Greek word atomos, which means indivisible. So it means it's an operation where you can observe kind of the state before the operation and the state after the operation, but you cannot observe any kind of in-between state. It just happens in one operation, basically. So that also means it's an operation that is race-free. And that also means that it's an operation that is, by definition, thread-safe, right? So that's a very good property because you can then use it in concurrent code. So what about shared pointer? Is shared pointer actually thread safe? Who thinks it is? 1. Who thinks it's not?
What do you mean by thread safe?
Who thinks that both options are wrong? Yes. So the standard actually doesn't say very much about thread safety of shared pointer. The only thing that it says is that for a shared pointer, changes in use count do not reflect modifications that can introduce data races. That's the only thing that the standard says about this. So basically what this means is that if you have a shared pointer instance and you, for example, take a copy of it, which is going to increment the ref count, and then on another thread, you also take a copy of it, which is going to increment the ref count as well, that's not a data race. You can do both of those things on 2 threads simultaneously. And then at the end, both copies are going to point to the same control block, and all threads are going to agree that the ref count in the end is 3. Okay? So that's what it means that if you modify the ref count, that's not a data race. So taking these copies on different threads is is allowed is not a data race. That's guaranteed by the standard. This is what it looks like in code. You have a shared pointer. You can take one copy of the shared pointer on one thread. You can take another copy of that shared pointer on another thread. And then you can do whatever you want with those two different instances, putter 1 and putter 2, on those two different threads, and you're not going to have a data race there, right? So that's all fine. That's what this means. It gets more interesting if you flip around the second one, and instead of taking a copy, we actually assign to that shared pointer instance, right? So what we're doing now is on one thread, we are reading from the pointer, we are making a copy, and on another thread, we're modifying a pointer. So we are assigning a new value into that same instance. Who thinks this is okay? Okay, still one person thinks that's okay. Well, no, that is undefined behavior. That's a data race. You are reading, you're reading from a shared pointer, and you're modifying the same instance of a shared pointer on another thread. That is an operation that not only modifies the refcon, but it also modifies the pointer to the control block, right? Because you're overwriting the shared pointer. So that is a data race. And I was kind of confused by this at first. Like for a while, I was very confused about this, but then kind of in the end, it made a lot of sense. And we actually heard this morning in the keynote where Dave Abrams was saying, well, think about this as an int, right? It's like an int. Like it's the same thread safety that an int does. You can copy an int, or you can read an int from like multiple threads simultaneously, but you cannot copy an int in one thread and write to the same int on another thread. That is a data race. And even though in a shared pointer there's a little bit more going on under the hood with the ref count and everything, essentially it is the same logic as with an int here. And I think that actually makes it kind of very straightforward to understand what is and isn't thread safe here. So of course this is a solved problem. Like if you have that race, there is a way to solve this. There's obviously the manual way. You can solve this yourself by taking the shared pointer and wrapping it, for example, with a class that then has a mutex, so you can guard the whole thing with a mutex. You can have a shared pointer and a mutex guarding it next to it, and you can put that in an object, for example, and then solve the problem that way. But we also have a solution in the standard to solve this problem. Actually, ever since C++11, which is when we got shared pointer, we also got the atomic underscore freestanding functions, which also have an overload for shared pointer. So we have, it's a bit of a weird interface, but it has been around since C++11, right? So it was always there with shared pointer. There are this set of freestanding functions which are atomic underscore something something, the operation that you're doing, like load, store, compare, exchange. And then it has this weird interface where it takes a pointer to a shared pointer as its first argument. But this interface allows you to do atomic operations on shared pointers, right? So you can write a value into it, read a value out of it, do a compare exchange, and that's going to be atomic, and it's going to be race-free. So with that, we can solve our race in this way. Instead of doing a copy and an assignment, we can do an atomic load and an atomic store on the other thread, and that is thread safe, right? Unfortunately, this does work, but it has at least two problems. One problem is that it's kind of unsafe by default, right? You have to remember to use these freestanding functions. If you just have a, because they work on like naked shared pointers, right? And if you have a shared pointer and you access it from multiple threads simultaneously, you have to remember to use these freestanding functions. And if you don't do that, by default, you just use the naked shared pointer, and by default, that's a race. So you kind of have to opt into the safe behavior by remembering to use the freestanding functions atomic underscore. And if you forget that to do that in one place, then you have a race. Yes?
Yeah, I just wanted to mention, if at least one thread doesn't do it, all the other threads, no matter how careful they are,
yes.
so
Further is absolutely correct. If even one thread forgets to use the freestanding functions, it doesn't matter what all the other threads are doing, the whole program has a race. And there's another reason why these freestanding functions are not a good solution, which is you can't really implement them efficiently because they are freestanding functions and they just take a pointer to a shared pointer, right? So you can't have a mutex that protects that shared pointer next to it, right? It has to work with any shared pointer. So the implementation strategies can be either, you have some kind of lookup table where for every shared pointer you get passed in, you kind of store like a mutex, and you have like some kind of map between like shared pointers and mutexes. Or from what I heard, what implementations or some implementations are actually doing in practice is you just have a global mutex for all the shared pointers, which is not a very efficient implementation strategy, but apparently at least some standard library implementations do that. So that is not, you can't really implement this very efficiently. And so because of both of these problems, this just isn't a good solution. So actually, all the way back in 2014, Herb Sutter proposed a better solution to actually wrap this into a proper type that handles this. And so he proposed specializations of std for unique pointer, shared pointer, and weak pointer. The committee did like that proposal, but they didn't like the fact that there are specializations of atomic. So they said, well, it's not really consistent because std is supposed to work only with trivially copyable types, and shared pointer obviously is not a trivially copyable type. So you shouldn't really have a specialization for this. We should have an extra type called atomic underscore shared pointer and weak pointer. So Herb revised his paper, and now it's called atomic underscore unique pointer, shared pointer, and weak pointer. And there was a later paper also with wording for these three types. We didn't get atomic unique pointer, but we did get atomic shared pointer and weak pointer, which then in 2015 was put into the concurrency TS. The concurrency TS in 2015 had these atomic underscore shared pointer and weak pointer types, which looked like this. And then again, a couple years later, once we had a little bit of experience with the concurrency TS, Alistair Meredith came along and said, hey, it would be really good to actually have this in standard C++. But we need to fix a few things, like the concurrency TS version wasn't quite right yet. So actually, we shouldn't have atomic underscore shared pointer because that's just odd. Like the interface is the same as for std. Why do you have like another name? It should really be a specialization of std. So if you went back to the original proposal from Herb and said this should be a specialization of std with angry brackets instead of underscore, and also fixed a bunch of other stuff in there. And that was accepted for C++20. So we have it now in the standard, in the most current standard, C++20. We have std shared pointer and std weak pointer. And so with that, we can solve that race condition that we saw earlier like this. So we actually now use the type std shared pointer. And if you use that, that is safe by default. There is no way atomic shared pointer can have a data race. And then we can use load and store. Hang on a second. We can use load and store explicitly like this. Or we can actually omit this and just use the kind of copy constructor and assignment syntax, which for std is doing exactly the same thing as the load and store. I prefer to write load and store because I like it to be visible that it's a std type, but ultimately it's a matter of code style. So you can write this, which looks exactly like the very first version of this code, except it's now an atomic shared pointer, and that is safe. Yes?
Does it support copy initialization? Because normal std doesn't. It requires direct initialization. You can't write like atomic of int equal 1. You have to write atomic of int braces 1.
I think it does, but I'm not 100% sure. Let's check afterwards. I think this should be.
He's not doing from pointer to pointer. Like if you do
This is
like atomic of int, you can't write atomic of int equals 0. You have to write atomic of int.
Well, you I think you can.
You can?
Yeah, atomic int
I thought it's explicit.
equals 0. Yeah, I think you can. Let's.
Okay, let's table
This is like an API question, so let's
table it.
look at it later. It's not really relevant for what I'm talking about here. But yes, we should clarify this. Anyway, so we have atomic shared pointer now in the standard. If you look at CPP reference, well then at least 2 major implementations, GCC and Microsoft, already support this in their newest versions. So everything's great, right? Like the problem is solved. Well, not quite, because turns out this is not lock-free. So neither on MSVC nor in GCC, these asserts fail. Both the runtime version and the compile time version of these asserts fails. Why do we care about this? So let's talk now about the third bit, which is the lock-free, which is not the same as atomic. Lock-free means something else than atomic. It means, well, exactly what it says. There is no lock, right? So it means you achieve this without using something like a mutex. Instead, you're using atomic operations that are supported natively by your CPU. So it's kind of a platform dependent thing, what atomic types or operations you support or don't support. And lock-free is really great for things like low latency and real-time applications like games, video games, audio processing, which is kind of my background, high-frequency trading, embedded applications like cars, elevators, robotic arms, that kind of thing. Because of, well, at least two reasons, right? Why we couldn't use why we can't use the previous version, which is atomic but has a mutex, is the first one. In those kind of low latency and real-time applications, you have a deadline. You basically have a limit on how much time an operation can take before it needs to be completed. And if you're waiting on a mutex, you're waiting for another thread to complete something, you don't really know how long it's going to take. It's not deterministic, right? So you might run out of time and fail your requirement to produce a result within a millisecond or a microsecond or whatever it is. And the other problem with mutex is that not only do you have this problem that it's kind of, you don't know how long you're going to be waiting for the mutex, but also you get this problem of priority inversion, which means if you have an application like audio processing or like some financial stuff where you typically have something like a hot path, right? That's where the stuff happens that needs to be fast. And then you have typically one like high priority thread, which is doing that. And you have a bunch of other threads, which are kind of low priority and kind of communicate with that thread and maybe slide data in and out in some kind of lock-free way. But like you have this like hot path. But mutexes don't care about things like thread priorities, right? So if your hot path waits on a mutex, then that mutex might be held by a low priority thread. That low priority thread, because it's low priority, might be scheduled out by the thread scheduler and then, not run at all, and maybe something else runs. And so you get this problem of priority inversion. And if you do lock-free programming, you can avoid all of these problems, right? So which is why for these kind of applications, lock-free is really kind of a hard requirement. Yes, Andreas.
So about the suitability for real-time applications, like lock-free is a term that is used differently by different communities, but like in some cases there's the distinction between lock-free and wait-free, where technically in lock-free you can still have unbounded wait times on a specific thread, which can be a problem for real-time.
Yes. So to repeat the comment, basically, Andreas pointed out that there's actually the distinction between lock-free and wait-free. And if you have lock-free, you don't actually have this guarantee that you have a bounded amount of time at which your operation completes. That would be a wait-free operation, which is kind of more restricted. That's correct. I mean, this is kind of a different talk to talk about this stuff. But yes, lock-free gives you a bit of a weaker guarantee. The guarantee is that at least one of your threads progresses, right? But it's still better even in these applications, because with a mutex, for example, you can end up in a situation where you're waiting on a mutex and then the kind of low priority thread or some other thread that is holding the mutex maybe is going to be suspended or somehow die. And then you are just stuck and you will never make any progress. Whereas if you have a lock-free algorithm, if it's not wait-free, for example, it can have a cast loop in it, and we're going to see that later, right? Technically, yes, it's not bounded how long it's going to take, but the probability that it's going to keep spinning goes down over time, and you never end up in a scenario where if one thread basically dies or gets suspended, then the other thread can't make progress. So you're still guaranteed, even though you don't have this absolute upper bound, you still have the guarantee that at least one thread is going to make progress.
Like in particular, like with regards to the priority inversion problem, if you're on an actual real-time operating system, unless you take special care in your mutex implementation, the priority inversion can lead to an unresolvable deadlock, which
right.
then you're
right.
screwed, right? So there, the lock-free.
So it is a very interesting topic. There's a lot of subtlety to this. This talk is not about that. This talk basically says, when you have considered all of this, you will realize that for these applications, a lock-free implementation is what you want, and a not lock-free implementation is not really suitable. Okay. But yeah, there's a lot of nuance to this, and obviously, yeah, we can talk about this a lot more, but this is kind of not the purpose of this talk. But happy to talk about this later. So here's a use case for specifically this kind of lock-free atomic shared pointer that I presented at my very, very first conference talk ever, which was CppCon 2015, where I was actually still working in the audio industry. And the example here is like some kind of synthesizer where you have a GUI thread and audio processing thread, and on the GUI you have some kind of envelope that you can tweak with your mouse, and that's going to change the way the synthesizer sounds, so that's a lot of fun to kind of interact with. And then you have this audio thread which has this real-time audio processing callback that just keeps producing your sound kind of in real time. So that thing cannot wait on a mutex because it's a real-time callback. And now you have this object, which is this kind of envelope, and you need that to know what sound to create. So you need to kind of share this object in between these two threads. And you cannot use mutexes because on the audio thread you cannot lock. And you also have to worry about the lifetime of this object, right? So then in that talk I was talking about how that's a problem that kind of occurs quite a lot, and what you end up doing if you want this to be lock-free, you kind of have to then use an atomic raw pointer because you don't have an atomic shared pointer, and then you kind of have to manage the lifetime manually, and that basically there's no way you can get this right. This is like so messy to do this manually that, like, yeah, this is not a good idea. And then what I said in this talk was actually one of two kind of major blunders that I committed at previous conference talks where I just gave bad or wrong advice. And I did that. That happened to me at least twice. This was one of those instances where I said, well, to solve this problem, basically use these freestanding stdatomic underscore functions, which back then, that was 2015, we didn't have atomic shared pointer yet. We only had these freestanding functions. So I said, well, just use those and that solves the problem, because that way you can use shared pointer, it's going to manage your lifetime and everything. And I completely overlooked that already back then, like we had these, but that was never lock-free in the standard library implementations. So then if you would do this in your synthesizer, then your real-time audio callback would end up waiting on a lock, and then your synthesizer is probably going to glitch instead of producing sound, and nobody's going to want to buy that. So that is not a good idea. Later, I learned another thing, which is actually there's a whole other programming pattern which is actually a lot more suitable for this particular case, because in this case, you also have another problem. If you share the kind of manage the lifetime across threads, you want to make sure that the real-time thread, the one that can't lock, is not the thread that's going to end up having to destroy the object, because destroying the object is a deallocation, which is, again, not lock-free, so you cannot do this on a real-time thread. To make sure that the real-time thread is not the one who ends up destroying the object. So there is a pattern for this, which is called RCU, which is very much suitable to this problem, which I was not aware of at the time, which is kind of better than using atomic shared pointer here. But there is another use case for atomic shared pointer, which is lock-free structures, and particularly lock-free structures and the ABA problem, which if anybody who has done lock-free programming in C++ knows that this is a major pain in the neck. ABA problem is basically this thing where one thread changes the value and then changes it back to what it was before, and then the other thread doesn't realize that anything has changed at all, and then the whole state of your data structure is completely messed up, and everything is going to be very sad. And that tends to happen in C++ quite a lot when you design kind of a lock-free algorithm. And now we come to the second major blunder that I committed during a past conference talk. It was a talk at ACCU 2017, which was called Lock-Free Programming with Modern C++, because of course it's a good idea to talk about that if you don't know what you're doing. And I was talking about a lock-free queue that would work with multiple readers, and I had this like code on the slide, and I was like, okay, yeah, this is the solution. I tested this. This works. Just use this. And then somebody came on stage and said, well, I'm not sure this is quite right. I think you overlooked something there. And then I was like, I don't know, this looks right to me. I showed it to like 10 other people who also looked at it, and they also said it's fine, so, so we didn't quite resolve our kind of differences there on stage, but then of course later when the talk was published, on the comments in the YouTube, YouTube video, people then pointed out that, well, you didn't account for the ABA problem, therefore your data structure is wrong. And unfortunately, ABA problem is something that you can't just, easily patch, right? If that's something that you haven't accounted for, then that kind of invalidates your whole algorithm. So you have to like redesign the whole thing, and it's going to be very, very complex. So if you look at lock-free queues that exist out there that are known to be working and used in practice, like for example the Moody Camel lock-free queue or the Boost lock-free queue for the ones that have multiple readers and multiple writers. You look at that code, you're going to see that it's very, very complex. They have like all the like load and store operations and compare exchange. They have these like long kind of cast loops with like multiple atomic operations inside. It's very, very, very complicated. And kind of the main reason why these algorithms are so complicated and so hard to get right is because you have to account for two things, right? So you have to manage, in like a lock-free queue, for example, you have to manage the lifetime of your elements across different threads, so that's complicated. And you have to solve the ABA problem, right? Turns out, atomic shared pointer kind of encapsulates both of them, right? Because shared pointer kind of takes care of the lifetime, because that's what it does. And it also doesn't suffer from the ABA problem because shared pointer actually knows about the identity of the object that it's pointing to, right? So you're not going to have this typical problem where you have like a queue with like indices and then you have like the same index. So something changes it back. You have the same index, but actually you're in a different state. So that can't really happen because you know the identity of each object. So you know if the object has changed, you know it's a different object. So atomic shared pointer kind of neatly encapsulates both of those aspects that make lock-free programming so complicated. And so if you write lock-free data structures on top of atomic shared pointer, they actually become really short and nice and elegant. Yes?
So about the shared pointer not suffering from the ADA problem, what about the situation where I point to something, it's then freed, and then it gets allocated again at the same address? Can I then get an ABA problem again?
So Andreas was asking if you can get an ABA problem if an object is going to be freed and then allocated again. Well, if it's going to be freed, it means that that shared pointer instance doesn't exist anymore, because otherwise it wouldn't be freed. So
okay, so that's what's
so that's the thing. Basically, you don't have just like an array of objects and indices into it, and then you have to manually like figure out when to delete them. But like shared pointer just knows that it's going to delete it whenever there's nothing anymore using that shared pointer instance, right? So
the control block could still be alive. The object would be gone, but the control
yeah,
block,
yeah, sure, but that's usually not a problem.
because control block is held by the weak pointers.
Yes. So okay, if you have weak pointers in there, that's like it adds a little bit of complexity. But let's not go into designing lock-free data structures on that level here, because then we're going to spend the rest of the talk talking about that. But yes, it's an interesting problem. What I want to show here is a lock-free structure which is built on top of atomic shared pointer, which actually comes straight from Herb Sutter's atomic shared pointer proposal. This was his motivational example. And it's a concurrent stack which supports push front, pop front, and also kind of traversing the stack and finding an element in it. And so these three operations, and you can do all three of them from as many threads as you want simultaneously. And it uses this atomic shared pointer here. And the whole thing fits on a slide. It's actually complete, and Herb says that it's also correct, and I believe him. So all the complexity of like managing kind of the ABA problem and the lifetime and everything is kind of encapsulated in this like atomic shared pointer here. And it's not just the concurrent stack. There's also an implementation of a lock-free queue, which is also built on top of atomic shared pointer, which is similarly short and kind of elegant. They're probably not going to be the fastest implementations that you can find, but I think they're kind of nice because they're very simple. So atomic shared pointer can make lock-free programming like really easy and elegant because it kind of encapsulates a lot of the complexity. So then I was watching another talk by Fjodor, which is actually right here in the room, at CppCon 2017, where Fjodor was talking about kind of RCU, kind of the other the other algorithm that we're not going to talk about in this talk. And basically he was talking about different building blocks that you can like use as a basis for log-free data structures and log-free algorithms. And he was saying that you basically have RCU, you have hazard pointers, you have atomic shared pointer, and they all have different trade-offs and different properties, and you might want to choose one or the other depending on what problem you're solving. And also kind of emphasizing this idea that an atomic shared pointer is like one of those basic building blocks for log-free algorithms that you might want to use. And the thing that I found really striking about, one of the things that I found really interesting about this talk is that Fyodor was talking about this atomic shared pointer, which is log-free here. Like, oh yeah, of course, just use a log-free atomic shared pointer. Everyone has an implementation of that lying around. You can just use that, right? We have that in our toolbox. I was like, well, okay, where did he get an implementation from? That's interesting. And then I was like, in 2019, well, now it's in the standard. Surely, the standard atomic shared pointer is going to be log-free because it has all these properties, and as Fyodor was explaining, you can use it as a building block for log-free structures, and it's super cool. It makes everything nice and elegant, and it's very powerful. So surely this is what we're going to get in the standard library once it's in C++20, right? Wrong. So I was, very optimistic, and I went on Twitter again, 2019, before C++20 came out. But when we already knew that it's going to be in the standard, and standard library vendors will have to ship it, and I was like, when it comes out and when you're going to ship your implementations, dear implementers of GCC, Clang, Microsoft, etc., surely you're going to give us a log-free implementation because it's awesome and it solves all these problems and we can really use it for all of these nice things. And the response I got from STL here, for example, is, well, no, and also I don't think you can even implement this. Like, I don't think a atomic log-free shared pointer is actually implementable because, if you think about it, well, you have the control block pointer and then you have the ref count, and you kind of need to modify both of them. They're like different things, right? And you need to modify both of them simultaneously. How could you possibly do this? Like, I don't think this is implementable. But then it was further saying, of course, I'm already doing this. This is great. And then also I found a blog post by Anthony Williams, who is also obviously the godfather of concurrent programming, wrote the book about, literally the book of concurrency in C++. And he was also saying, well, atomic log-free shared pointer, it's going to be more complex. It has more work to do. Like, it's probably going to have more overhead because of all these atomic operations in the uncontended case. But it's awesome for contended cases where, you need performance. So my library is going to also ship with an implementation. And I have an implementation of log-free atomic shared pointer. But of course, it's not open source. So I couldn't look at it. So I was like, well, so on the one hand, I have these really intelligent people who are telling me they have implementations somewhere. I can't look at them. And then all these other people that I also really respect, the standard library implementers, who were saying, no, we're not going to do this, and also we don't think this is implementable. And I was like, there's a little bit of a contradiction here. And then I was like, okay, I really need to dig and figure this out. Yes?
Okay, so I want to make a comment to clarify basically what, I had it a little bit easier, well, a lot easier time when I was doing this, because I was talking about atomic shared pointers specifically designed for implementing your particular data structure. I implemented intrusive log-free. Intrusive is the keyword. A shared pointer. After you say intrusive, and I can do it because it's designed for that list, for that stack, for that whatever, at that point it does become trivial. You pack both reference count into one place, and performance-wise, it just wipes the floor with the generic implementation.
Okay, so Fyodor's comment was that he had an implementation that was intrusive and specific for the data structure that you were working on, which makes it a lot easier than in the generic case where you want to implement the whole interface of the shared pointer.
And way faster.
Yes, and also way faster.
It's important if you're building log-free data structure.
Yes. So a more special implementation is a lot faster than the generic one. All right. That's a very good comment. Thank you. I did not know that. That's very illuminating. But let's talk about the generic standard version, because that's kind of what this talk is about. So status quo today is Microsoft ships with a not lock-free implementation. GCC, the kind of pre-release trunk version, has a implementation which is not lock-free. Clang doesn't have an implementation. I don't know if they're working on one. Unfortunately, Marshall isn't here, or any of the other Clang people, I think. But I'm very curious if they plan to implement this, or what their plans for this is. But it turns out that there are actually 3 lock-free atomic shared pointer implementations that are free and open source and that you can look at. There is one by Anthony Williams, which is not his full kind of just thread library commercial version, which is kind of a proof of concept version that he has out there, which you can look at. Then there's another implementation by Facebook's Folly library, which is actually in production, which was written by Dave Watson, who doesn't work at Facebook anymore, but is now maintained by David Goldblatt, which is also free and open source, and you can look at. And finally, there is a third implementation by Vladislav Tsubashev, who was also spending some time understanding this problem, and he looked at Anthony Williams' implementation, and he didn't like it. And then he looked at Folly's implementation, and he didn't understand it. So then he just wrote his own, because that's what you do. So there are all 3 of them, and it was actually really, really useful to look at all 3. And I actually want to say a huge thank you to the maintainers of all of these 3 implementations, or the authors. So Anthony and Vladislav, and then in the case of David, is the maintainer. Because I've written to all of them, and I really tried to understand what's going on in their code, because it's not really obvious. And all 3 of them actually replied very patiently to my emails and explained how things work, and I learned a lot from these interactions. So it's actually really cool that people are so helpful, and they reply to you, and they take their time to explain things to you. That's one of the things I really like about the C++ community. And Vladislav also actually has a blog post about how his implementation works and about the whole problem, which is here. Unfortunately, it's in Russian, so I can read it because Russian is actually my mother tongue, but you probably cannot. So maybe there's Google Translate that can help you, I don't know. But it's a very, very cool blog post that's called Thread-Safe Lock-Free Shared Pointer, an adventure for half a year, and where he kind of writes about his experience of like implementing this. So yeah, another very good blog post about this. So let's figure out how we would actually implement this and whether or not that's actually implementable, because that's kind of the $1 million question here. So we come back to this slide here, which is how a very basic stripped down kind of generic shared pointer would work. So you have this pointer to the control block, and the control block has a ref count, a pointer to the object, and then obviously the value of the object itself. Now, if you want to modify this shared pointer, for example, by loading or storing or doing something like that, in a lock-free atomic way, basically what you need to do is you need to increment or decrement the ref count and simultaneously modify the control block pointer at the same time in a lock-free atomic operation, even though both of those variables are, at different points in memory, right? Like the control block pointer is in the shared pointer instance, and then the ref count is in the control block itself. So they're like completely disjoint, like different places in memory, and you have to like modify both of them simultaneously, lock-free atomically. So what you need here is a double compare and swap, right? This is what this operation is called. Turns out there's actually one processor which supports this. It's the good old Motorola 68000. It has a instruction called cas2, which does exactly this. It atomically modifies 2 separate memory locations at the same time. So on this particular CPU, implementing an atomic lock-free shared pointer would actually be pretty trivial. Unfortunately, no modern CPU supports this instruction, which is very unfortunate. So you cannot do this. So it seems that we're kind of stuck here. Yeah. Do you have a question or a comment?
It's a basic question. So I understand how the ref count has to be changed.
Yes.
Why do you need to change the CPU pointer to what?
Well, okay, so the question was, why do you have to change both of them? Well, you have a shared pointer, and now just assign a different shared pointer to it. And you want that to not race with reading that same shared pointer on another thread. So what does it mean if you assign a new shared pointer to it, right? So you need to decrement the ref count because you're reducing, so that shared pointer is not going to refer to that control block anymore, so you need to reduce that ref count. And also you need to like store the new control block value in it. And you need to do both of those things atomically.
And increment the new ref count.
And increment the new ref count, well, that you can do kind of before. So you don't have to do all three of those things. But you can increment the new ref count in one step, but then the next step you need to do the other two things simultaneously. Does that answer your question? Assignment, yeah. But also, yes, so yeah, assignment. So we don't have double compare and swap, but we, yes.
A quick comment to this. It's always okay to increment a little bit too early. The problem is if you decrement a little bit too early because somebody dies.
Yeah.
Yes.
If you increment a little bit early, you're holding the object a little longer alive than it should be, and no big deal.
Yeah.
Yes, so if the ref count, the comment was that if you increment early, it's not going to do any harm, because if the ref count is higher than it's supposed to be, that's never going to do any harm. But if it's lower than it's supposed to be, then the object might be destructed while somebody's still reading it, and then you're going to get undefined behavior.
Resets need these two, right? Reset.
Sorry, reset. Shared pointer reset decreases the ref count and sets the control block pointer to null, yes. So you also run into the same problem, basically with every operation.
You don't, right? Because you can null the control block pointer, and then at your leisure.
No, well, you could have two threads that are trying to do this simultaneously. So there will still be going to be a race. Anyway, so there are like enough cases where you would have to kind of, maybe not for every operation that you could do on a shared pointer, but at least for some of them, you will need to modify both of those variables simultaneously. So we agree on that, right? And you can't do that. So what modern CPUs do have is something that's called a double with compare and swap, which is different from double compare and swap, which is basically that you can atomically modify two adjacent memory locations at the same time, two adjacent words, right? So on 64-bit, you can modify 128 bits next to each other in one step. So basically the constraint is that the two pointers, or the pointer and the counter, need to be next to each other, which they're not. So how do we solve this? Well, there is a solution, and it's an algorithm that's called split ref count. And it's not an algorithm that you will find a lot of material on. It's not like, I'm not going to find this probably in a kind of classical book about programming. So David Goldblatt, the maintainer of the Folly implementation, put it like this. He said, like, it's sort of a folk algorithm. Like, there are a few people who kind of know how it works, and that like knowledge is kind of being passed on, from person to person. That's kind of how this works. Well, I actually did find two references to split ref count. One in this blog post by Dmitry Vyukov, and then another. It's also mentioned in Anthony Williams' concurrency book, actually. In both cases, it's not in the context of implementing a shared pointer, atomic shared pointer specifically. It's kind of in a slightly different context. So it's not really exactly applicable to this problem, but it's kind of the same idea. So what is the idea? How are we going to do this? So basically the idea is that you split the ref count into a local ref count and a global ref count. So you have a ref count which lives in the control block, which is the global one. And then you have a local ref count, which lives in the atomic shared pointer instance itself. So you might have multiple of those if you have multiple instances referring to the same control block. And then basically those two together kind of tell you what the actual ref count is. And the idea is that you kind of first modify the local ref count, because that's something you can do atomically together with the control block shared pointer. And then you kind of try to synchronize the local and the global ref count in a second step. And that step is kind of where all the complexity is going to be. So if you look at some code, if you want to implement this, you will have something like this. I call this counted pointer here, which is this structure that has a control block pointer and a local ref count both together. And you put that on an atomic variable. And let's just assume for now that This is going to be lock-free on your platform because you have double with compare and swap. We're going to talk about this later, whether that's actually the case. That's also a very interesting question. But then let's assume that you can do this, and then basically the algorithm is you first increment the, like, for example, if you want to do a load, so you take a copy, and it's kind of similar for all the other operations, but like the load is just the simplest one. You first increment the local ref count. So you actually want to increment the global ref count, but you can't do this immediately because that's not going to be atomic. So you first increment the local ref count, then you increment the global ref count and decrement the local ref count. And then if that kind of fails because the local ref count, that object has changed by another thread, then you kind of try again. So you kind of do this in a cast loop, right? So, and so basically if you manage to decrement the local increment the global and decrement the local ref count, and no other thread has modified this object in the meantime, then it's success, and then you have successfully increased the global ref count, and then you can just return your copy of the shared pointer. And if you have failed, it means that another thread has modified the state of that object at the same time, so you need to kind of roll everything back and try again. So you're going to have a cast loop around this whole thing. So let's look at how you would implement load, because that's the simplest of like the three: load, store, and compare exchange. Oh, there's also exchange, so there's like 4 of them. And this is basically the Anthony's implementation and Vladislav's implementation. They both do essentially this. They're like the actual code looks different, but like the essence of the algorithm is the same. And with Folly, like there's a little bit of more stuff going on there, but it's also essentially the same idea. So all three free and open source implementations basically use the same idea. So how do we implement our load? So first, yes, we increment the local ref count. This is how it works in Anthony's implementation. That's using a double with compare and swap. Annoyingly, you can't just increment it because it's a 128-bit variable, and there's no 128-bit increment instruction. So you kind of have to increment the local ref count, and at the same time make sure that nobody has changed the control block pointer, which is the other half, right? So that's why in this case you need like this cast loop. But then in the end, you have just incremented the local ref count. So that's for step 1. Step 2 is, okay, you got like a new valid internal state, which is an incremented local ref count. So you're going to take a copy of that, and that's kind of the shared pointer you're going to return in the end. And then, so what you actually want to do is you want to increment the global ref count. So you increment the global ref count here, and then you try to decrement the local ref count here again. And you do that in a cast loop, and if here you notice that somebody has modified the control block pointer while you were trying to decrement the local ref count, you just kind of have to roll back and start over. And there's another case which is a little bit more tricky, which is actually handled differently in Anthony's version and in Vladislav's version, which is if you already like modified the global ref count, but then somebody modified it, then it means that you were not the thread that was supposed to modify the global ref count. So you again need to kind of roll back. And then if another thread did modify it, you have to like go around the loop again until you are the thread that succeeds. But if there's no other thread, then you just going to go through it once and then you succeed. And at the end, you just return a shared pointer that has this new state.
When you unroll your own modification, when you unroll your +1, if you drop it to 0, then you're the one deleting it.
The comment was that if you're the one dropping it to 0, then you're the one deleting it. Yes.
So you should be deleting it at that point.
Well, this is loading, right? So you're taking a copy. You're taking a copy of the state and you're returning that copy. So you're not.
Right, but
Yeah, if you're doing that decrement, then you just did an increment.
You did an increment before.
You did, but somebody else might have done a decrement, which means you're going it back down.
But if it was 1 before, then you are the only instance that has a pointer to that control block. So that case cannot happen. You are the only instance that owns it.
While this is going on.
No, because you made it strictly before you in the thread. You incremented it.
Right. So I do have a lot more slides. So
Okay.
let's maybe discuss the details of it later. And also, this is just the load. This is like the simplest of the three. Like the store is more complicated, the compare exchange is even more complicated. So basically, the purpose of this slide is not to talk you through the complete implementation, but to just convince you that this is implementable. It's not easy, it's complex, but it is implementable. This is kind of what I'm trying to convince you of. This is implementable, and people have done it. And now I'm kind of in the process of doing it again and learning how to do it properly. So if we have this kind of algorithm and this kind of pattern of like with the cast loop where you do the local and then a global ref count, that's kind of repeating throughout every like the other operations will have similar cast loops in them, and then there's like more stuff. And but each one of those accesses, whether it's like load or store or whatever, will have at least 3 atomic operations. At least like 2 of them will be in a cast loop. So in the best case, you'll have 3 atomic operations. In the worst case, you will be in this cast loop for a while and do a lot more of them. So in any case, even if there's no contentions, this is going to definitely be slower than the mutex version, because taking a mutex, if there's no contention, that's very quick. Whereas even if there's no contention, in the best case, you still have to do at least 3 atomic operations in this version, and that's going to be slow. So on average, this is going to be slower than the lock mutex version. But it is much better than the mutex version under high contention, because you never end up kind of waiting forever on the mutex, but there's always going to be one thread which is going to be the next one that gets to succeed in the cast loop. So the overall system is going to make progress. That's kind of this lock-free guarantee that you get. And then Folly actually does not what we just saw. It has like another implementation on top, so another optimization on top of that, which is really, really clever. So whenever you do a load, instead of incrementing the ref count every time and do this dance every time, they kind of just increment the global ref count up front for at least as many, like some number k, which is bigger than the number of threads that you expect poking at this. So you kind of increment it up front, and then you kind of just and then you increment the local one up front as well, and then you kind of just decrement the local one every time you take a new copy. And that's just one atomic operation, and you don't have to go to the control block pointer at all until you run out of these like kind of pre-incremented ref counts. So that's kind of a really clever optimization that they do on top. The trade-off here is that if you do this kind of in advance increment of like kind of reserve some ref counts, then basically your use count member function, which returns the current ref count, is going to be useless because it's just going to have some big number in it. Bryce has a comment?
This optimization is done in each thread, so like each thread does this batching for future loads
Yes.
in that thread. Okay, so it's not global cross thread. It's just like each thread is like, I'm just gonna.
Oh, so the question was whether each thread is doing this.
Yeah.
So you increment, as far as I understand, and like look at the Folly code, it's not very readable, but like the way David also explained it to me and what I can see is you do this increment in the global ref count and also in the local ref count. And then you kind of decrement, and then so basically you have like these, so each instance has like its own batch of like pre-incremented local ref counts that you can keep decrementing. And if you run out, if that thread runs out of local ref counts, then it goes into the global one and tries to get more.
Right.
And then there's like, you can have different implementation strategies when each thread, like what number you have to reach. Like in the Folly version, if you get to half, then you start going to the global ref count again and getting more counts. But then like that's probably not optimal, because like depending on what you're doing, multiple threads might start going to the global ref count all at once. So you don't want that. You want probably some kind of tail off strategies, something. You can do this in more clever ways than this.
The idea is that like each local ref count is sort of getting.
Yes, each local ref count, the idea is that each local ref count has some kind of like pre-increments that it can just use, and only when it runs out of those, it needs to go to the global ref count again to get more. So that's kind of the optimization here. And there's different flavors of this as well. This is just kind of the basic idea. So this is what Folly is doing, what the other 2 implementations are not doing, which is kind of pretty clever. All right, so now we've done.
Read-write log on the target essentially, while you are. So each of the not all threads modifying one instance will have the same, will share the buffer.
Right. And then there's also like what do you do if you run out? I mean, there's also different things you can do. You can also say, well, then we're going to drop to like a mutex implementation or something like this. There's like different flavors of this, but we can talk about this later. Okay, so we've done all of this work. Do we now have a log-free atomic shared pointer? Do we have a working implementation now? Well, turns out not quite, because this is not everything that a shared pointer does. Like if you look at the standard shared pointer interface, there's quite a lot more features that it supports. So it supports weak pointers, so you have to have weak pointer support to like break cycles, right? So you will, in addition to the ref count, you will also have a weak count there. And then the shared pointer also supports a custom deleter, and it also supports a custom allocator. And so far it's not a problem because all of the stuff is in the control block, right? So that's not a problem. But there's one more feature of std shared pointer which is going to be the problem here, which is each shared pointer instance also has a pointer to the object itself, right? And that might or might not point to the same object as the pointer in the control block. And why is that the case? Well, one reason is that shared pointer has this thing called the Aliasing Constructor, which I don't know who's familiar with that? Okay, a few people. So basically the idea is that you can have a shared pointer that shares kind of the lifetime ref count management of one object, but actually is pointing to another object. And you can construct it like this. And typically this other object will be it has to be something that has the same lifetime as the original object, because otherwise you would probably have a bug, right? So typically it will be something like a member of that object, like here, right? So you share, like the shared pointer kind of manages the widget, so it's going to destroy the widget when it goes out of scope. But if you dereference it, you're going to get a pointer to the J member of widget, right? Now you might think, well, okay, this is this weird case where the shared pointer has a different pointer than the control block, but this is really exotic. Like I've actually never seen this to be in production. It's kind of a rare case. Maybe we don't need to support this. Okay, yes, some people have used it in production. So there are use cases for this. I would say it's pretty rare, but it is useful. But there is a much more common case here which runs into the same problem, which is this. And this case, definitely a lot more people have run into. It's the case where you have a pointer to derived and then you have a shared pointer to base, and it still works. If you have a shared pointer to base and that goes out of scope and like the ref count goes to 0, it's going to call the deleter of derived and not the deleter of base, right? That's the destructor. That's really, really important. And with shared pointer, that just works. And that comes up a lot more often. Like imagine, for example, you have some kind of GUI library where you have all kinds of widgets. You have like a hierarchy of widgets, right? Different ones, right? You have a widget base class, and then you have like sliders and buttons and whatnot. And it's like a polymorphic class hierarchy. It's one of those cases where shared pointer is actually used for this kind of, to manage this kind of stuff. And so that case is there, and it's important. You need to support this. And then you run into this problem that all of a sudden you have 3 things you have to modify atomically, right? So you have control block pointer, you have the ref count, and then you also have this pointer, this aliasing pointer, which maybe points to the object or maybe points to a base class. So I should say, why is this a problem? Because if you have a pointer to base and a pointer to derived, that's not necessarily the same address, right? You might have multiple base classes. So then they in general don't point to the same address. So you need to store them separately. And so you have this pointer to base, in this case, for example, on the left, and the pointer to derived on the right. And so you need to now swap 3 things at the same time atomically. And well, there is no triple width compare and swap. So how are we going to do this? There are different solutions to this. So Anthony Williams' version has a solution which is pretty clever. So basically, what he's doing is that he's instead of storing a pointer to the object here, he's storing an index into this data structure, and it's this kind of very simple kind of linked list which can only grow and not shrink. So it's so it has just 2 operations: push back and find, basically. And that is so simple that you can implement it just with raw pointers, and it's like 30, 40 lines of code. It's pretty simple to do. And so if you have that kind of very primitive log-free data structure, you can basically use that to store aliased pointers, basically that are associated with every control block. And then in your shared pointer, you only have to store an index into that list. And you can kind of, if you're on a 64-bit system, you can cram this, you can cram both of these things, like the ref count and this index, into one kind of pointer-sized variable. So that's going to be one word, and then your control block pointer is going to be the other word. So you have two words, two width, right? So that works. I think that's a really clever solution. And then basically, if you create more shared pointers, with more different alias pointers that all point to the same control block, so you have 3 slots for these alias pointers kind of pre-allocated there in the shared pointer. And then if you have more aliases that you are constructing, then basically you're doing like a pushback into this log-free data structure. And it kind of keeps growing. So you have a bit of runtime overhead. If it gets long, you need to like traverse it. So that's not going to be super efficient, but like it works. But there is one problem here. If you are creating these alias pointers here and putting them into this linked list structure, that's a memory allocation, right? And memory allocation is not log-free, right? Because you're calling malloc. And if you're, I don't know, if you're Google and you have like TC malloc running, and you probably don't care about this too much because you have your whole allocator under control. But if you are just an audio plugin, for example, running on some average user's laptop, you cannot use malloc you cannot call malloc on the real-time thread. So and the problem is that this can occur anywhere where you're like modifying the shared pointer value, right? So anywhere where you're creating a new shared pointer and putting that into an atomic shared pointer. So you have to do this on the store, on the exchange, and on the compare exchange. So none of those operations will actually be log-free in general, because you might end up calling malloc if you need to have like another alias pointer here. So that doesn't quite work. And and that same Twitter thread we were talking about, this JF actually pointed this out. And Anthony Williams said, yes, my implementation needs a log-free allocator for this like extension blocks, that's structure. Otherwise, it's not log-free. And well, yeah, it's a bit of a problem, right? Because like you might have a log-free allocator. It might be possible to do this in your application, but that's not really the case in general. And also that doesn't really fit into the API of shared pointer. How do you thread this through the shared pointer? You're going to have like a very custom thing going on there. It's not really this kind of generic tool anymore. So this is not really a workable solution here. My suggestion how to fix this would be, well, you can move the allocation from the atomic shared pointer into the shared pointer itself. So you do the allocation every time you create a new shared pointer instance that's aliasing. And then by the time you store it into an atomic shared pointer, you don't have to do that anymore. You don't have to do the allocation anymore because you've already done it. So in this way, all the atomic operations are going to be log-free. The problem is that there is going to be an overhead for in the shared pointer constructor, whenever you create an alias shared pointer, even if you don't use that shared pointer together with atomic shared pointer. So that's a price that you have to pay. I did come up with a solution for that as well. Just a couple months ago, I had this idea how to solve this. And I was like, I think this is really cool. And then I told Anthony about this, and he was like, oh yeah, I had the same idea a few years ago. And that's actually in my like closed source, like better implementation of atomic shared pointer, I used something like this. So that was interesting. Kind of we independently had the same idea here. But the idea is basically that you observe that if you have an alias pointer, typically you're going to be pointing into, that's not going to be like a completely different memory address, right? You're going to be pointing typically to a member function or a base class of the original object. So the difference in address is not going to be that large. So what you can do is you can compute the pointer difference between those two pointers, like the object pointer and the alias pointer. And then if your object is not bigger than 4 gigabytes, which I really hope it's not, you can fit that pointer diff into 32 bits. And then you can fit your local ref count into the other 32 bits. And then you can store the whole thing into 64 bits. And then you can store it together with the control block pointer in the 128 bits. Without having to do any allocations or any additional data structures at all. And only if if the two pointers are more than 4 gigabytes apart, then you have to do this dance of like with the data structure that we saw before. But that's going to be an extremely rare case, right? I would bet that it's probably never going to happen in practice. Even if it does, the allocation will still happen in the shared pointer constructor. So you're still going to be lock-free whenever you do the atomic stuff. And then you just have to do like a bit like flag to indicate whether or not you store the pointer difference or you store like an index into this structure for the alias pointer. And you can use like one of the alignment bits for that or something. So that works. Do we now have a lock-free atomic shared pointer? Are we now done? Well, there's another problem. This relies on double width compare and swap. Do we have double width compare and swap? And this is kind of also very confusing, or it was for me when I was like trying to figure this out, because I heard very different things from very different people. Some people said, oh yeah, of course, double width compare and swap, like every CPU can do this these days. And there were other people who were saying, no, this is really not portable, and like, no, it's also very slow and like not portable, and you can't do this, and really you should stay away from it. And I was like, okay, again, like different people tell me very different things, like what's the truth here? So I did some digging. And I actually, a couple months ago, wrote a long blog post just about double width compare and swap, which you can find on my blog, timur.audio. I'm just going to do like an extra quick summary of that investigation, which is basically, yes, double width compare and swap exists basically on CPUs. On x86, you have this instruction compare exchange 8B. On x64, which is, of course, like the platform we care about a lot, you have instruction for this called compare exchange 16B. On ARM, you have this also both on 32-bit and 64-bit. Unlike the newest chips, I think it's also one instruction like in Intel. In general, like on other ARM processors, it's different. You have this thing called like load, lock, store conditional, which is kind of a bit more complicated series of instructions where you actually also have a difference between weak compare exchange weak and compare exchange strong. They do slightly different things there. And it's like a whole other topic how this works. It's actually really, really cool and very, very powerful mechanism. But that's not the talk about this. The whole point is that, yes, all modern CPUs have these instructions. On x64, like every chip has this since at least 2008. There are some AMD chips which are older than that, which lack this instructions, but then Windows doesn't even run on there, for example, because Windows requires double width compare and swap since Windows 8.1. If you don't have that, it's just not going to run. Same with macOS, it requires it. Like Linux can run on these like old chips that don't have that instruction, but basically, yeah. So basically, every modern CPU is going to have that instruction, and the performance. Well, I mean, I did like a very kind of simple benchmark of this, and turns out, well, on x64, like double compare and swap is on average like twice as slow as compare and swap, which makes sense because it's doing double the work, so makes a lot of sense. And actually, I tested this even with like a 10-year-old Mac Mini that I had lying around, and it was also just 2 times slower. So I think it's not 5 times slower, it's not 10 times slower. It's kind of not abysmal performance. And on ARM, the difference between single width and double width was even smaller than this. So we don't have like a catastrophic performance problem here. The more interesting question is, does stdatomic use these instructions? If you use stdatomic, is this going to compile down to these instructions that we all have in our CPUs and that are actually exactly what we need here? Or in other words, is this static assert going to succeed? And this was me when I was looking at this a few months ago, and like, well, CPU supports it, so surely stdatomic is going to just emit those instructions, right? Wrong. So I tested this basically on every compiler and architecture that was kind of relevant for me. I did this with Apple Clang on kind of the different Macs that I had lying around at home, and I did this on kind of normal Clang, GCC, and Microsoft on Godbolt. For kind of all of these 4 platforms that are kind of relevant. And it turns out, well, short version is on 64-bit, double width compare and swap is not portably supported because of ABI. So it's another one of those sad cases where implementers choose ABI stability over performance. So that is very sad. Possible solutions, well, we could implement our own stdatomic Yes?
This is the kind of thing that gets kicked to libatomic if the compiler doesn't.
Yes.
So would libatomic then use the double-wide comparison?
No, well, my understanding is that libatomic implements like, so what the standard, what it does if you don't have these instructions is that it falls back to an implementation that is using mutexes. So whenever this like static assert fails, the std-atomic thing is still going to compile, still going to have the right semantics, but it's going to have mutexes inside, which is exactly what we don't want here, right? Or spin locks, or some mechanism that is not lock-free. And so my understanding is that this is what libatomic does. Like this is kind of the fallback implementation. And maybe I think on GCC in some cases you get like, so the weird thing, I mean, really, this is a long blog post. Please read it. Like there's this weird thing where like on Linux, for example, you could actually test at runtime if you have double root compare and swap. But they don't even do that because even the runtime is lock-free version is still returning false. And it's really, Bryce has a comment.
So there is a thing that we could potentially do that might work, which is you could, inside of libatomic, you could not use mutex for this case, and you could use double width compare and swap. Is always lock-free would have to lie there. And that should be fine. Because unless you have somebody that was statically linking libatomic, which I don't even know if you can do, then you'd be fine as long as, because everybody would be either using an old version of libatomic, which would use the mutex-based version.
Yes. So I'm not going to summarize everything that you said because it was a lot, but like we need to talk about this. I need to understand this a little bit more. Basically, what happens is that on Mac, you're fine because like macOS just requires and assumes that double compare and swap is there. They know exactly what CPUs they run on. On Windows, they could do the same thing because Windows actually requires double compare and swap. Because of ABI, std-atomic just doesn't do that, and adding that support would break ABI for std-atomic. Interestingly, it does work on Microsoft for std-atomic ref because that's a new thing. So they don't need to break ABI for that because it's a new thing. There is no previous ABI. So it works with the std-atomic ref, but not with std-atomic. And Microsoft, it's still kind of easy to get around this because there is a Windows intrinsic, like Windows API function, which is called interlock compare exchange 128, which is doing this. So you could like wrap that and get this. But on Linux, as Bryce was explaining, like it kind of falls back to libatomic, and you don't really know what's going on there. In general, it will not emit these instructions. And there might be a way we could in the future work around this, but also I think Linux wants to support these old CPUs that don't have that instruction, maybe. I don't know. Like, let's talk about this later. It's an interesting conversation. And I really wish we could fix this, but like status quo right now is that this is not, double compare and swap is not portably supported, full stop. So what we could do is we could either implement our own std-atomic, which is, as I said, on Mac trivial, on Windows doable, on Linux I have absolutely no idea how to do this. I think it's a huge amount of work. I'm not the expert for this. Or you could, well, on GCC, I don't know. So atomic ref works on Windows. I don't think atomic ref is lock-free on GCC. So no. And also you have these GCC kind of underscore like lock-free atomic something functions, and they also don't do the right thing. So basically today, the only other option you have is don't use double with compare and swap. So how do we do this without double compare and swap? Well, there's actually a strategy. It's called a packed pointer, and it's used both by Vladislav's implementation and by the Folly one. So the Anthony Williams one uses double with compare and swap. The other two use packed pointer, which is 64-bit only, and it's basically exploiting the fact that x64 actually doesn't use all 64 bits of an address. It uses a 48-bit address space, which is still plenty. And you have a bunch of unused bits. You have like the alignment bits, which are going to be 3 or 4, depending on what the max align T is. But you also have these 16 bits at the top, which you can use because they're not used. And actually, they do now, so now Intel has now 5-level paging, which in theory, which goes up to 57 bits for the address space. And there is already hardware, I think, that supports that. And there's already a Linux kernel that supports that. But that is still kind of not a problem because user space applications will still only see the 48-bit address space because, surprise, surprise, Hiram's law, there are a lot of applications that rely on those 16 bits. You know, not being used. So I think we're going to be good with that approach, at least for a while, if we are not doing kernel stuff, but we are in user space. I think we're good for this for, I think, at least another decade or two. The same story really on ARM. Again, they have a 48-bit address space, and they are kind of enlarging it now, but not for user space stuff. And with this, basically, if you want to implement this, it's going to look something like this. So you're now packing, we have this like packed pointer thing where we have one atomic kind of pointer-sized integer value, and we are packing both the control block pointer and the local ref count into the same pointer, and we're using 16 bits for the ref count, the unused 16 address bits, and the rest is the address. And whenever you access the pointer or the count, you have to do this offset or the mask. And then if you set them, you have to do it the other way around. You can probably imagine how this looks. This is also interesting. So here, we're kind of offsetting, we're kind of like shifting this address, right, to like shift out the 16 bits. And then we're returning a pointer. So it's like a hidden reinterpret cast in there, right, because we're casting this UN pointer t to a t star. But this is actually one of the pretty much the only case where reinterpret cast is actually okay, because the address that we're returning is actually an address where there's actually an object of type t living at that exact address. So that is fine. So with this, you can basically implement the whole thing and not use double compare and swap, because it can cram everything into 64 bits. The only problem, of course, is so now you have this value, just this one value, which contains both the pointer and the local ref count in one variable instead of these two fields, right? So you don't need double compare and swap. The only problem is, what do you do with aliased pointers now? So you definitely don't have any space to like save like an index into this like linked list thingy, or like to save a pointer difference. There's no space for it, right? So what Vladislav's implementation does is that it just doesn't do anything about it. If you try to create a shared pointer to base and give it a pointer to derived, it just crashes, which is unfortunate. Folly does handle this case. So what they do is they, if you have an aliased pointer, they kind of wrap the control block into another wrapper, which for them it's just a shared pointer. It's like another level of indirection. And then you have like a bit, you use like an alignment bit to like tell it, okay, this is an aliased pointer, so you need to go to this wrapper and then get the control block pointer from there. So you have to do this like indirection. This works, but of course, allocating this wrapper is again a memory allocation. So again, you know, if you're not running with like our own allocator where we control the world, we cannot do this, unfortunately, because otherwise the atomic stuff is again not going to be lock-free because you're calling malloc in there. So again, you do have the solution. Folly is not doing this, but David said, yeah, it kind of seems to make sense for your use case. You can again move the allocation from the atomic shared pointer into the constructor of the shared pointer. So you're going to keep the atomic ones out. So they're going to be lock-free. They're not going to allocate. And then, of course, the problem with this is that you're going to pay this overhead. Every time you create a shared pointer with an aliased pointer, you're going to have this extra allocation in the constructor. So that's the price you're going to have to pay for having the atomic versions lock-free. And this time, there's no way, there's no trick to get around it, right? Because we don't have any space to save any extra information in there. OK, so that's kind of where we are. Here's a little overview over the three kind of open source implementations. I know that there's at least one closed source implementation, which could also be put on this table, but I don't have that. I don't have access to that. There are probably other implementations somewhere closed source living in some company's code base. Further, you said you have one, but it's kind of more specific, right? It's an intrusive one.
So I have one that basically works for like node star.
Right. Okay.
And the first thing it actually requires, I mean, the way I've done it is, you know, the same way as STL does. Like, it requires node to have certain interface.
Okay,
Like
so it's a very
STL,
specific
it
one.
won't compile if node doesn't have a function like reference count.
Yeah. But if you want like a generic implementation of atomic shared pointer, the way it's defined in the standard library, there are three open source implementations. None of them are really portable. Anthony's requires double with compare and swap. Vladislav's requires this kind of pointer packing. And Folly's one, that's actually the most ridiculous thing. So Folly had this requirement for some reason that they had to use like actual std shared pointer. So the other two, they have like their own shared pointer, like which has the same interface as std shared pointer, but it's like a custom thing that knows how to interact with the atomic version. Folly's version uses std shared pointer. And so they are specifically using the GCC, the libstd C++ implementation. And they have this like thing around it where they do this like trick where you can access private members by doing this explicit templates instantiation trick. I'm sure some of you have seen this. So they can reach into the guts of like std shared pointer and like modify the ref count in there and do everything they need to do. And it's really dirty and like it only works on GCC. They say, if somebody wants to implement the same thing for Clang or Microsoft, we accept pull requests. So yeah, so it is definitely also not portable. It just works in one compiler. None of them are lock-free in the case of alias pointers. Anthony Williams is the only one that's mostly standard conforming, implements almost the whole interface of std atomic shared pointer. Vladislav's is very, very incomplete. Like there's a lot of stuff missing there. There is no exchange. Like a bunch of the constructors are missing. Like the whole like alias pointer stuff just doesn't work at all. Folly's is a bit more complete, but they don't have a weak pointer, for example. But also on the other hand, Folly is the only one that's production. That's like production quality that's used in production. Kind of the other two are kind of proof of concept implementations. So with both of the other ones, I found bugs within 5 minutes of using them. Like I found bugs or missing things or things that were just wrong. So Folly is the only free and open source one which is mature and production ready. All right, last section of the talk. I have 10 minutes left. Benchmarks. So I did some benchmarks. And actually, this is another thing where I would really appreciate some feedback because I don't think I quite figured out yet how to benchmark this properly. So what I did there is I have this atomic shared pointer to some object. And then I have just a bunch of threads which are just pounding that atomic. So you have like a cast loop where like each thread tries to set this atomic shared pointer to whatever value that thread has. And they're all kind of fighting to like be the one. Like basically there's like n threads pounding this atomic shared pointer. And that number is variable. That goes from 0 to a lot of threads. And then I have one thread which, while this is going on, trying to do an atomic load and see how long that takes, an atomic store, see how long that takes, an atomic compare exchange, see how long that takes, and a loop, an atomic compare exchange weak in a loop, and see how long that takes until it succeeds. So that's the thing that we're going to benchmark. So I think it's probably not the super best way to benchmark this. So if anybody has better ideas, please let me know. This is kind of the first thing I could come up with. This is what it looks like. So one of the two compilers where I can actually compare different implementations is Apple Clang, because Anthony Williams compiles on that, because it supports double compare and swap on Mac, if you have that. And then Vladislav's implementation compiles there as well. So we see here, basically, this is like the number of threads, and this is how long it takes. And we see here that on average, like this is where the blob is. This is kind of the median runtime. The version with the locks, libc++, that's the version with the locks. And it's like the freestanding one. They don't have the atomic shared pointer one. I just wrote a wrapper around the freestanding version. But it's kind of, so on average, the one that uses the mutexes is a lot faster. But the worst case is a lot worse, right? So sometimes we are very unfortunate. We end up waiting a lot on this mutex, so that the top of that black bar is very high. Whereas the two lock-free implementations, they are slower on average, but the worst case is a lot better, right? And that's really what we want. And you also see here that Vladislav's implementation is kind of 2 to 3 times faster than Anthony because A, it doesn't use W compare and swap, so that's faster. And then if you don't use W compare and swap, there's another optimization you can do where if you do if you increment the local ref count, you can now do that as one atomic fetch add because it's just one word that you're manipulating. So you don't have to you get rid of one cast loop and you just replace that with a fetch add. So that's another reason why this is faster. So this is the load. The store, actually, Vladislav's implementation uses a very weird and unfortunate implementation for store, which I think can be done a lot better, where store is basically a compare exchange loop, which is weird. So that one in Anthony's version is a lot more efficient. The compare exchange is kind of similar to the load, and then if you do this in a loop, that's where we see the performance is actually really, really bad for all of them. Because if you do a compare exchange on an atomic shared pointer in a loop, you basically have nested loops, right? Because every operation has like this cast loop, and then you stick that in an outer cast loop as well. So that's really a lot of instructions. That's going to be very slow. So if you use atomic shared pointer, you probably want to avoid putting a cast loop around it, because it's essentially going to be a nested cast loop. That's going to be very slow. The other compiler where I can do some benchmarks is GCC, because Vladislav compiles there and also Folly compiles there. In fact, this is the only compiler it compiles on. And it looks kind of a bit similar, except surprisingly, I didn't see a performance benefit from this like batch ref counter implementation, which is like really clever, and it's supposed to make the load a lot faster. Not the other ones, but the load ought to be a lot faster with Folly than with Vladislav. But I don't really see this here, which is odd. And maybe I just didn't find the right way to benchmark this yet. So I need to do more work on trying to figure out how to benchmark this properly, because I think I'm kind of compounding two effects here, right? So on the one hand, I'm kind of measuring just regular kind of contention on an atomic, right? And on the other hand, I'm trying to also measure how fast the operation is at the same time. So it's kind of conflating two different aspects of this. I really don't know how to benchmark this better, but I think there must be a better way.
You're not measuring throughput, you're measuring latency.
Yeah, of course. I don't care about throughput. I'm not like Google. I don't run a server. I only care about latency. Yes.
Well, and I suspect that implementation that they did improve throughput more than latency.
Okay, well that would make sense for Facebook, because they would care more about throughput.
Because it's the first time you have to do it, you have to do it. It's
Okay.
but after you've done it, everybody else who comes in gets a free ride because you bumped up the reference count so high that basically accidental deletion is almost impossible.
Yeah. Okay, so I have 3 minutes left, so let's talk about this later. But I think this is an interesting topic to discuss later. Okay, I'm kind of at the end. Takeaways. Is a lock-free implementation of STD atomic shared pointer possible? And hopefully I have convinced you all that it's complicated, but it is possible. If you have either double load compare and swap or free pointer bits that you can use, right? So you need to have one of those two things to implement it. And if you don't have double load compare and swap and you're using the free pointer bits, then how many bits you have basically determines how many threads you can have simultaneously accessing this lock-free. Because if you run out of ref count, then you kind of just have to block and wait, right? And the other problem with if you don't have double compare and swap is that if you then still want to support the aliased pointer case, which is really important because of this base-derived kind of case, which is quite common, then you will incur an overhead in every shared pointer constructor every time you create an aliased pointer if you want to keep these allocations out of the atomic operations, which you want. And then there's a bunch of kind of conformance versus performance trade-offs here. Like one example is that if you implement this refcount batching that Facebook does, you don't have a usable use count that you can expose to the user. And there are like other things that you can do or not do, and it will kind of restrict kind of the API level, surface level that you can kind of meaningfully implement. But of course, the real question is a lock-free implementation of STD atomic shared pointer possible in STD without an ABI break so that standard libraries can actually do this? I guess for Microsoft and GCC, it's too late because they already have their not lock-free implementations. Maybe it's not too late for Clang. So the question is, but is it possible without changing the ABI, breaking the ABI on STD shared pointer itself, which we definitely don't want to do? And that's, again, the Twitter thread from before where Anthony Williams was saying, well, his implementation requires the shared pointer needs to have knowledge of the split ref count. That's how his algorithm works. So you kind of have to re-implement split shared pointer in order to work with this atomic shared pointer. But that's not the case in general. That's the case for Anthony's version of this. But Vladislav's version doesn't need this, and Folly's version also doesn't need this. And they actually do use std shared pointer, right? They literally use std shared pointer. So in general, yes, you can implement this without an ABI break on std shared pointer. You still have to worry about atomic, as we discussed before, because that has to, there's all these trade-offs. Either you need to implement support double compare swap or not. But anyway, you can use this, you can implement this without breaking ABI on shared pointer. So maybe for Clang it's not too late. I don't know if they're working on implementation or not. Okay, so as I said, this is work in progress. So there is future work for me to do. I need to figure out how to benchmark this better. I need to actually finalize my own implementation, which is still very much work in progress. It's not ready to be put on GitHub yet. What I want to do in there is I want to make it switchable between double with compare and swap, and you can either do that or the pointer packing, so you can kind of choose, so it's going to be more portable. I want to make it actually lock-free in the non-allocating for the case of the alias pointer, as we discussed. I kind of want to experiment further with like refcon batching and whether it's actually a benefit for decreasing latency, which there was a comment that maybe it's more kind of for improving bandwidth, so something to look into. And then if I have a complete working implementation, I obviously want to put this on GitHub, so you all can look at this. And maybe one of the things I also need to do, which is kind of a very ambitious long-term goal, which I hope I don't need to do, is to actually re-implement atomic as well, to force it to use double with compare and swap. I very much hope somebody will do this for me, or maybe there even is a solution out there, but I'm not aware of one. So this is again the table for like the 3 existing open source free implementations, and I kind of want to be here, right? So I want to make it more portable. I want to make it actually lock-free even for the alias pointer case, and I talked about how I'm going to do this. I want to actually implement the complete API, and hopefully one day somebody will actually use this for something. So this is kind of still work in progress, but hopefully at some point in the not too distant future, I can put this on GitHub and it's going to be complete and I can share it with you all. So yeah, this is all I have for today. Thank you very much for listening.